Okay, welcome back. So last time we finished with a statement of Hoeffding's inequality, and this time we are going to go through the proof of that. So let me share screen. And let's begin by recalling the statement of the inequality. So we have a sequence of IID random variables. The random variables are mean mu, and they are bounded. They take values in this bounded set 0 to 1. And we are looking at the probability that the sum of n of them deviates from its mean by at least nt. Or if you divide both sides by n, we are looking at the probability that the sample mean of the first n random variables deviates from the true mean mu by at least t. Okay, and the theorem says that the probability of this event of the sample mean deviating from its true mean by some constant amount t decays exponentially in n, the number of items in the sample, and the decay rate grows like t squared. The most important aspect of this is really the decay, that the decay is exponential in n. This is the main message you should take away from. And then the exact rate of decay is a bit of a detail, but that's the exponential decay is the key message here. Okay, and we saw that the proof of this relies on the proof of a related lemma which bounds the moment generating function of a bounded random variable. So if x is a random variable with mean mu, and which is restricted to lie in this interval 0 to 1, then it's centered, the moment generating function of the centered random variable x minus mu decays like this, is bounded above like this. Okay, so let's prove this lemma in the remainder of this lecture. Actually, we are not going to prove quite this, but a weaker version of this inequality, where instead of theta squared over 8, we'll prove it with theta squared over 2. That proof is easier, and it also uses an interesting technique called symmetrization, which is interesting in its own right. So that's a reason to prove that as well. Before we turn to the proof of this, I need to tell you about Jensen's inequality. And that's an inequality relating to convex functions. So let's begin by recalling the definition of a convex function. And the simplest way to define it is by picture. So here I've drawn a convex function. And what makes this convex? What makes it convex is that if I pick any 2 points on the graph of the function, so here, so this is f of x, that's f of y. So I've picked these 2 points on the graph of the function. I draw the line segment joining them. Then that line segment lies on or above this function. Okay, so that's what it means for a function to be convex. So more formally, a function f, which maps the real numbers to the real numbers. Okay, it's a minor technicality that we allow infinity as a value, but you can ignore that for the moment. A real valued function f is convex if for all x and y in the domain and all alpha between 0 and 1, we have the following inequality. F evaluated at alpha x plus 1 minus alpha y is smaller than this right-hand side. Okay, so a bit more terminology. If I give you 2 points x and y, then this quantity alpha x plus 1 minus alpha y is called a convex combination of x and y for alpha between 0 and 1. So what in words, this is saying is that the function evaluated at the convex combination of x and y is bounded above by the same convex combination of fx and fy. So back to the picture. So here are x and y. Here's that convex combination alpha x plus 1 minus alpha y. For different values of alpha between 0 and 1, it'll give you different points here on the line segment between x and y. And the definition says that f evaluated at this convex combination, which lies here, is smaller than the convex combination of of f of x and f of y, which lies here. So this is alpha. So this point here is alpha times this point plus 1 minus alpha times that point, and it lies above f evaluated at the same convex combination. Okay, so that's the formal definition, and I hope that's clear both as a formal definition and as a picture in your mind. Okay, so that's the definition of a convex function. And then Jensen's inequality says that if x is any random variable and f is a convex function, then the mean of f of x is at least as big as f evaluated at the mean of x. And that's should hopefully also be clear from this picture. So let's go back down here. So suppose the random variable x takes only two values. It takes value little x with probability alpha and little y with probability 1 minus alpha. Then alpha x plus 1 minus alpha y is the mean of this random variable x. So the right-hand side here is the left-hand side here and the other way around. Okay, so Jensen's inequality is just the definition of convexity if the random variable x can only take one of two different values. If it takes only finitely many values, then again it follows from the definition just by induction. And if it takes infinitely many values, then you also have to use some continuity arguments or use a different way of proving it. But hopefully the intuition from the finite case helps you believe that this is also true in the general case. So that's Jensen's inequality. It's a very important inequality about expectations. Good. So now we'll be using this in our proof of Hoeffding's inequality, or the weaker version of Hoeffding's lemma. Okay, so let's. So I mentioned that we'll be using a technique called symmetrization, and this is how it works. So we have a random variable x, and we are going to let x prime be an independent copy of x, meaning that these two random variables are independent and they both have the same distribution, that of x. And so they also have the same mean mu. Now, if we apply Jensen's inequality to this convex function, so firstly you can check that e to the minus theta x is a convex function, either by using the definition or by differentiating f twice. You can look at that in the notes. So by applying Jensen's inequality to this convex function, we see that the expectation of e to the minus theta x prime is at least as big as e to the minus theta times the expectation of x prime, which is mu. So we get this inequality here. Okay. And now what we are really interested in is the expectation of e to the theta x minus mu. But let's start by calculating this instead, expectation of e to the theta x minus x prime. Well, this is e to the theta x times e to the minus theta x prime. Now, x and x prime are independent random variables, and it follows from that e to the theta x and e to the minus theta x prime are independent random variables. And recall as well that if we have two independent random variables, y and z, the expectation of y times z is the expectation of y times the expectation of z. So using that fact, we can write the expectation here as the expectation of e to the theta x times the expectation of e to the minus theta x prime. The second term here is bounded below by e to the minus theta mu. E to the theta x is a non-negative random variable. Its expectation is non-negative. So when we multiply both sides of this inequality by expectation e to the theta x, the inequality is preserved. And so we get that this quantity here is bounded below by expectation e to the theta x minus mu. Okay. We are trying to derive an upper bound on this moment generating function. And the first step is that this is bounded above by this quantity here, the symmetrized expectation. Okay, now let's look at the random variable x minus x prime. Our starting assumption is that x was bounded on the interval 0 to 1. So this new random variable x minus x prime is bounded and lies within the interval -1 to 1. That should be obvious. Okay, and since these have the same distribution and the same mean, the difference has mean 0. And finally, the distribution is symmetric around 0 because x and x prime have the same distribution. So x minus x prime and x prime minus x have the same distribution. So you have some random variable which is distributed between -1 and 1, mean 0, and some kind of symmetric distribution. You don't know the distribution, but it's symmetric around 0. Okay, now let's pick yet another random variable s. This is going to be independent of x and x prime, and it's only going to take one of two possible values. It can either take the value +1 or the value -1, and it's going to take each of these values with probability 1/2. Okay, s is a discrete random variable. X and x prime could be continuous. Now, let's look at the random variable s times x minus x prime. By the symmetry of the distribution of x minus x prime, whether you multiply it by 1 or multiply it by -1, it has the same distribution. So this random variable has the same distribution as x minus x prime. So we are interested in the expectation of e to the theta x minus x prime. We can replace it by another random variable with the same distribution. So we get that these two expectations are the same. And this is the key step. X minus x prime is bounded between 0 and 1. And so this expectation here is bounded above by the expectation of e to the theta s. This is not completely obvious. I'll refer you to the notes for the proof, but hopefully it's somewhat intuitive at least. Okay, so the key step is to bound the expectation of the random variable we are interested in, e to the theta x minus x prime, by the expectation of e to the theta s. But this, we didn't know the distribution of x minus x prime, but we do know the distribution of s, and this expectation is easy to calculate. S takes the value +1 with probability 1/2, which contributes e to the theta, -1 with probability 1/2, which contributes e to the minus theta to the expectation. Okay. And now the next step is to take the Taylor expansion of e to the theta here. So we get that this quantity is bounded above by half. E to the theta is the sum 1 plus theta squared over 2 factorial and so on. And here we have the sum 1 minus theta plus theta squared over 2 factorial and so on. And you can see that the odd powers of theta cancel from the e to the theta and e to the minus theta terms. The even powers add up. So what we are left with is the sum of theta to the 2n over 2n factorial, okay, over n. We only have the even terms in the expansion. And this, with a bit of manipulation, is bounded above by, let's take, so this is theta squared to the n. Let's take a factor of 2 from here up there. So it's theta squared over 2 to the n over n factorial. That's a bound, not exact. And now this quantity here, this sum over n, is just the Taylor expansion of e to the theta squared over 2. Okay, so we've proved that the expectation of theta times e to the theta times x minus x prime is bounded above by e to the theta squared over 2. And earlier we showed that e to the expectation of e to the theta x minus mu is bounded above by this. And so it is also bounded by e to the theta squared over 2. And this is what we wanted to prove. Not improve, prove that we prove. Okay. The original inequality is theta squared over 8. That's hard to prove. We set out to prove the weaker inequality theta squared over 2, and we have proved that. So that completes the proof of Hoeffding's lemma. Okay, so that was a somewhat involved proof. If it was a bit fast in the lecture, then go through it in the notes with full details. Now let's go back to the multi-arm bandit problem, and let's apply Hoeffding's inequality to a special case of this problem, which will be the case of most interest in the first half of the course. And this is the setting of Bernoulli bandits. Okay, so let me remind you of some terminology. We say that a random variable x has a Bernoulli distribution with parameter p, and we write it this way. If the random variable x can only take one of two possible values, 0 or 1, it takes the value 1 with probability p, and hence it takes the value 0 with probability 1 minus p. It's a model of a coin toss, basically, a toss of an unfair coin. So the coin comes up heads with probability p and tails with probability 1 minus p, and we denote heads by 1 and tails by 0. That's the Bernoulli distribution. So now let's consider a bandit with 2 arms, and the rewards on the arms are Bernoulli random variables. So what do we mean by that? x1t, the reward on arm 1 if you play it at time t. These are IID random variables, Bernoulli with parameter mu1. And the rewards x2t on the second arm are also IID, Bernoulli with a different parameter mu2. And the rewards on the 2 arms are independent sequences. So knowing that you got a certain reward, playing the first arm on time 3 tells you nothing about what your reward would be if you played the second arm at time 8. Okay, so that's the setting. Let's suppose, without loss of generality, that the first arm is better, but obviously the player doesn't know that, and they want to decide which arm is better. And they are going to use this very natural policy, which is, so at this point, we are not talking about regret yet. The player just wants to decide which arm is better. And they are going to play each arm some fixed number of times, n times, observe the total reward on each arm, and decide that whichever arm gave the higher total reward, or equivalently the higher mean reward, is the better arm. This is the most natural thing to do. Okay, so given this strategy, what's the error probability? What's the probability that when the player does this, they pick arm 2 as the better arm, even though arm 1 was better? What needs to happen for that? What needs to happen is that the observed mean on the second arm has to be bigger than the observed mean on the first arm. And we want to calculate the probability of that event, or a bound on the probability of that event. Okay, so I've said that already. So an error occurs if the sum, or if the total reward in n place of the second arm is bigger than the total reward on n place of the first arm. And we want to find a bound on the probability of this. So let's define yt to be this difference at the t time step. Notice that we only observe one of these, but depending on which arm we play, but we nevertheless define this random variable. No, my notation has changed. So t is the tth play of this arm. So we do indeed observe both of these. We observe the reward we got the tth time we played the second arm, and the tth time we played the first arm, and yt is the difference here. An error occurs if the sum of these yt's is positive. That's what this is saying here. x1t can only take values 0 or 1, and similarly for x2t, so yt can only take 3 possible values, -1, 0, or 1, and that's a subset of -1, 1, of the closed interval -1, 1. Okay. Okay, so in order to find a bound on the probability that yt is positive, we are going to use Hoeffding's inequality. But that would require yt to lie in not 1, and instead it lies between -1 and 1. So we first have to modify this. So the way we do that is define this other random variable zt in this way, and we've chosen this way to ensure that zt lies between 0 and 1. By adding 1, we have forced 1 plus yt to lie between 0 and 2, and dividing by 2 brings it to lie between 0 and 1. Now, what's the expectation of zt? Yeah, this is half of 1 plus yt. Yt has expectation mu2 minus mu1 because it's x2t minus x1t. Okay, and when does an error occur? It occurs if the sum of the yt's is non-negative, which in terms of the zt's is saying that the sum of the zt's is at least n over 2. This is what needs to happen. Okay, so now let's use Hoeffding's inequality to calculate this error probability. So the error probability is that the sum of zt, we have to center it by its mean, is bigger or equal to n over 2 minus the same thing. Yeah, zt bigger or equal to n over 2 is zt minus this, bigger or equal to n over 2 minus the same thing. So the n over 2 cancels, and so what we are left with is asking that this inequality hold. That's what the error corresponds to. And Hoeffding's inequality says the probability that the sum of n bounded random variables minus n times its mean being bigger than n times t is bounded above by e to the minus 2n t squared. So t here is mu1 minus mu2 over 2, and t squared is this. So this is the bound we get on the error probability of identifying the best arm after n trials. Okay. I mentioned in the last lecture that the regret in the multi-arm bandit problem grows logarithmically in t. And that's intimately tied up with the fact that the error probability decays exponentially in n. If you try each arm n times, the probability that you are going to be wrong about which arm is better decays exponentially in n. It decays pretty rapidly in n. And that's what it takes to ensure that the regret grows very, very slowly in t. It only grows logarithmically in t. Okay, so this is the preliminaries. So what are we? So let's summarize what we've done so far. We motivated the multi-arm bandit problem with a real-life example. We gave a precise mathematical formulation of the problem and the assumptions in the model that were needed for stating it. The main assumption being that in repeated pulls of a particular arm, the sequence of rewards form an IID sequence, and pulls of distinct arms give independent rewards, just the independence assumptions. Then we define the notion of regret as a metric for how we are going to compare different strategies. So the objective is to find a strategy which minimizes the regret. So that gave us a precise mathematical formulation of the multi-arm bandit problem. Then we went on to look at some inequalities, probability inequalities. So these are inequalities that random variables or sums of independent random variables deviate from their mean by a certain amount. So we want to say that sums of random variables concentrate very close around their mean values, and that's how we will learn which arm is better. And we make a mistake if what we observe deviates too much from where we expect it to be. And so we want bounds on the probabilities of such deviations. And we looked at a bunch of different inequalities. So that concludes the preliminaries, and next time we'll start with the first algorithm for the multi-arm bandit problem, which is called the UCB, or upper confidence bound algorithm. Okay, so that ends this lecture. I'm going to stop sharing my screen and see you next time.